This video is going to introduce how to solve absolute value equations both graphically and algebraically, and just seeing how that looks visually when we look at the graph. So solving absolute value equations, in order to have an absolute value equation, we need to have a variable that's inside the absolute value signs. So a simple example for this is something like the absolute value of x equals 9. So we should be able to solve this through inspection. Basically just look at this and figure out what our answers are. We know that the stuff inside of these absolute value signs, this x could simply be equal to 9 because the absolute value of 9 is 9. But also this stuff inside there could be a negative value of x. And if I solve for x now, I get x equals -9. Both of those should make sense because if we do a simple verification on this, we could see that if we go to verify, both of these make sense. Because if I put in a positive 9 in here, the absolute value of 9 is 9. This one verifies. If I verify the other one here, if I put in a negative value for the x, then absolute value of -9 also equals 9. Therefore, both of these solutions are valid. So when we go to talk about solving absolute value equations, we have to take this statement into consideration. When we solve these types of equations with absolute value signs, we have to consider, and for lack of a better word, I just say the stuff inside the absolute value symbols being both positive and negative. Then we solve both situations, and then we have to verify all solutions to make sure that none of the solutions we have are actually indeed extraneous. So to look at this in maybe a little bit more complex example, we have this. Let's solve 6 minus x, the absolute value of 6 minus x equals 2. And we're going to solve it, as I mentioned, we're going to solve it algebraically, and we're going to show it graphically after as well. So the algebraic solution to this, if I just rewrite this, says first thing we want to do is isolate that absolute value symbol. And if we look, it is isolated all by itself right there, so we don't have to get anything away from it. But I want to consider two cases now. I have case 1 where the stuff inside there, let's actually start, where the stuff inside there is positive, which means the 6 minus x, I want to consider this to be positive, and I want that to equal 2. And then the other case, we want to do case 2, I want to consider the stuff in there to be negative. So the 6 minus x, I want to say that stuff in there could also be negative, and that equals 2. So now we have two different equations that we want to actually start solving. If we look at it here, this is a positive 1. I'm just going to distribute that in. So that's 6 minus x equals 2. We now just use our algebraic skills. I'm going to first add the x to make it positive. So I get 6 equals 2 plus x. And now to isolate the x, I just take the 2 away. 6 minus 2, 4. So one of my possible solutions could be that x equals 4. And we're going to go solve the negative case now. We distribute in the -1. So I get -6 plus an x equals 2. This one's a little easier to solve with algebra. I simply add the 6 to both sides, and I have x equals 8 as another possible solution. So we considered both cases, positive and negative. We solved both, and now we want to go through and actually verify that these work. Now the verification, it's important to know that when we verify, we always verify back into the original equation and to what was given to us. So the first one I want to verify and see if it is indeed a solution is x equals 4. So inside here, 6 minus 4 in absolute value signs equals 2. Well, that is the absolute value of 2 equals 2, and we know that this is true. So this solution here, x equals 4, is a solution. And now we're going to verify the other one, x equals 8, and see if that's also a solution. So we have 6 minus 8 The absolute value of that should equal 2. And we could see that 6 minus 8 is negative 2. The absolute value of negative 2 is 2. This does verify. So x equals 8 is also a solution. A good way to end these, because there's a lot of work going on, if you were to show some work, is to just at the end make a simple statement. The solutions are x equals 4 and x equals 8. So we've proven that that actually is my solutions. Now, if I was to look at this graphically and prove this graphically, we're going to go into our calculator, and in y1, we put in whatever is on the left-hand side of the equal sign. So the absolute value of 6 minus x, and then y2 we put on the right-hand side, the 2. If you forget where the absolute value signs are, they're in your math button, which is right under alpha. Go over to number, and it's option 1 that says absolute value. That will give you those absolute value signs. So now if I graph these in my standard window, this is what I see. This V-looking graph is the absolute value of 6 minus x, and this is y equals 2. And the actual solution to these are where these graphs actually intersect. So we can see there's 2 intersection points. To find them, just second function trace, choose option 5. We want to find the intersection of 2 different graphs. And then it asks you first curve, just enter, second curve, enter. Let it get the solution for you. And we can see right here, it does show us that one of the solutions is x equals 4, and indeed, our cursor's on that one. So one of my solutions is x equals 4. Graphically, we can see that's where those 2 intersect. And now we want to see how to find that other one. We go back to second trace, go down to option 5 again, choose the intersect, but now if you want the other one, you have to get your cursor a little bit closer to it. So just scroll over with your buttons, get closer to the other intersection point, do the same 3 enters, and now again, you could see graphically that we have x equals 8, and there's the other solution as well, and it's flashing on there. So graphically, we get the same thing as we do algebraically, which is what we should have. So now let's move on to another example that gets a little bit more difficult, but not too much. We have, let's solve the absolute value of x plus 5 equals 4x minus 1. We're going to do it algebraically again, and then we're going to prove it graphically as a quicker method that we could do, and just shows a visual representation. So if we're looking, we want to consider this absolute value stuff. Since it is already isolated by itself, we wanted to consider the 2 cases again. Case 1, where that stuff inside there is positive, so the x plus 5, we want to consider that to be positive, and that will equal 4x minus 1. And then we want to also consider the other case where indeed that stuff in there is negative, so we're saying the x plus 5 is in the absolute value signs. I want to consider that to be negative, and I want that to equal 4x minus 1. So now we just have to go through once again, algebraically solve, distribute in a positive here, which leaves me with the x plus 5 equals 4x minus 1. I'm going to move my x to the right-hand side, so I get 5 equals 3x minus 1. Add a 1 to both sides to start getting x isolated. I have 6 equals 3x, and then you can see, if I divide it by 3, the possible solution is x equals 2. Now we go through on the other side, and we do the exact same work, distribute in a negative, so now I have negative x minus 5 equals 4x minus 1. I'm going to bring this x to the other side by adding it this time, so I have negative 5 equals 5x minus 1. Start isolating the x by adding this 1. And you see I have negative 4 equals 5x. The last step, divide by that 5, so I have negative 4/5 is also a possible solution to this algebraic or absolute value equation. But once again, we have to verify to make sure that nothing is actually an extraneous solution. So to verify, we always start back with our original equation, which in this case was the absolute value of x plus 5 equals 4x minus 1, and we test both solutions. So I'm first going to test x equals 2, so I'm going to put it in. 2 plus 5 equals 4 times 2 minus 1. I simply put in the 2 for both x's. Now you can see on the left-hand side I have the absolute value of 7 equals, here I have 8 minus 1, which is 7. Well, the absolute value of 7 is in fact 7. Therefore, x equals 2 is a viable solution. So now I go and check the negative 4/5 in the same manner. I'm just going negative 4/5 plus 5 in absolute value signs. Does that actually equal 4 times negative 4/5 minus 1? This is probably one where you'd probably want to put in your calculator just to verify it. It's going to make life a little easier. And you can see that this turns out to be the absolute value of 4.2, and this side turns out to be negative 4.2. So when I take the absolute value of 4.2, that's simply 4.2, that does not equal negative 4.2. Therefore, negative 4/5, this here, is not a solution. This is extraneous. So if we make our little statement at the end, just to make sure that we can keep our work together, the solution is only x equals 2. And if we were to look at this graphically, we should just see one intersection point between these two lines. So if we look on our calculator and enter the absolute value of x plus 5, and then 4x minus 1 and y2, look at your graphs, you can see that there is actually only one intersection point. So we're going to go and find this, and it should equal 2. So we do the same thing, second trace, choose option 5, first curve, second curve, guess, and you can see, in fact, the only intersection point is x equals 2. On our graph, it shows one intersection point. So we've proved it graphically, we've done it algebraically, we've verified our solutions, so now we're solving absolute value equations.